Thanks, Ryan, for the introduction. After 1 week and working very hard, it's time to be back to linear quadratic so that we start from crash. So it's a great pleasure and a great honor to be here. I would like to thank the organizers for the invitation. Last year was on very complicated stuff, so that's why this year is on linear quadratic. And the videos are online, and all the slides are already in the website, so you can download the slides and then follow here together with us. So there will be 4 lectures, and all of them on linear quadratic. It's the first time I do this. I think we will have enough time to go in all the details. We want explicit solutions. I want each of you, by the end of this week, to be able to compute explicitly a manifold game or manifold type game problem with the closed form solution, so that this will help us to understand what is going on. Okay, that's the goal of this lecture. And manifold games or manifold type games are mainly based on differential games. I thought it could be interesting to look at differential games. So I found this paper. This is 1925. It's probably not the first one, but this is differential game. So it's about duopoly models to start with 2 agents that are on a market, and they are producing at this cost. This is the cost function for agent I to produce a certain good. It's quadratic. It's fantastic. It's in our setup. And the price dynamics, look at here. The output, the total, you want to match demand to be equal to supply, is equal to a certain coefficient times P. P is the price. And then you have the derivative of P plus a constant there. So if you look at it, it's just P dot equal to demand supply minus A times P. So that's our differential equation. Now, each agent is going to maximize, okay, each agent is going to maximize the profit. So price times quantity that is producing, U1, minus cost of production. So there are 2 agents, and each of them is maximizing its own utility. This is differential game, right? 1924. Now, is there a concept of Nash equilibrium there? Because we know that Cournot's let me make this bigger. All right, this is the profit function. Reward for player 1, and the other one is reward for player 2. You want to define Nash equilibrium concept for this? Well, he has defined it here. Of course, the name is not Nash equilibrium, but it does the same thing. So problem 1, I'm back to problem 1. I will zoom that. Look at this problem. Let's have the price at time t1, okay? Then player 1 is maximizing his profit, fixing the choice of player 2. And do the same thing for player 2. 2 is maximizing pi 2, fixing the choice of player 1. It says as not subject to variation. So it means you freeze the choice of the other player, and you are maximizing your profit. What's the difference between this and Nash equilibrium? Nothing, right? That's Nash equilibrium. Okay? So the author solved this equilibrium problem in open loop. We now use Pontryagin maximum principle to do so, open loop. And he found explicitly And he was even able to add memories in the price. So the price tracks the past prices and so on. Okay? You get some kernels. I don't want to go into details, just to show you that it was there. And if you are interested in, I will upload this one again, so you can look at that. So that's our first example of linear quadratic differential game. He extended it to any number of agents at the end of the paper. So this is arbitrary number of agents. Okay, and you have the solution there. It's pretty impressive. I get inspiration from that work. Now, what is Manifold? What is differential game in practice? I will stop here for this example. In practice, I found some videos for you guys to start with after lunch. So the first video is about a predator and prey model. Okay, that's already over.
Giant tree valleys. Usually they are solitary hunters, but about 50 of them have come here from neighboring reefs, attracted by this abundance of potential prey. The fledglings stay out of the water if they can. They even drink on the wing. If the Trevally are to catch one now, they have to up their game. So there is a fish here that amazingly has a brain capable of calculating the airspeed, altitude, and trajectory of a bird.
Okay. It's very interesting, right? Predator and prey model. So there is a pursuer and evader, and they have different objectives, obviously. And that's a differential game. Now, another differential game that I found in nature is another predator-prey model, a tiger and a duck. That's my favorite example.
Welcome to Fight Day. It is duck versus tiger. The tiger is running to left this fast, but the duck fucking vanishes. He's like a little Houdini, creating illusions to trick the gullible as fuck tiger. He even has He's like, come on, you big pussy, I'm just a duck. I'll help you out, mate. I'm over here, you fucking dumbass. This way, I reckon you should have been born a snail. The tiger.
But it's still interesting to watch. And then he gets impatient. So now he's getting impatient because he doesn't see. And then he will try to jump. But miss the duck. It will reappear somewhere there, and so on. So I stop here for this example. we try to understand this dynamics. Of course, you need underwater dynamics, and I don't have any notions in physics to write down the forces, because it's not classical forces, it's underwater forces. So I talked to people in physics, and we are trying to write down the time of capture. In this example, it doesn't happen because it doesn't have enough energy to track the duck. And at the last, you will realize that it's gonna to let this one go. And then another example, now with multiple predator, is this one. You see now there are a bunch of tiger against the duck, so they will be able to catch up him this time, okay? But there will be tons of them. An army of them, and they will be able to catch up, okay? So I stop here. Interesting, right? So that's differential game. Now, I don't write any equations to illustrate what differential game is. Let me move to examples for Manifold games. So the first example is School of Fish. That's extremely popular. In the website, the announcement of the summer school, you have something like this. But except that the predator is not there. That was for bird. This one is for fishes and shark. All right? So they run away when the shark is coming. And we want to, the School of Fish, we could probably model with Manifold games and so on. But now we have a big impact from the shark, the predator, that's trying to catch some of them. Right? This is definitely a Manifold object, right? Now we put two sharks against that population. And that will be in another video, the second video. So if you had a chance to go to Australia for a conference, you could stop by to the zoo and watch these things. So two sharks, and then the School of Fish, and we look at how they try to run away from the sharks. We have done Manifold games for it, but we got inspiration from this model. I don't know if you see. So the first one is somewhere here, and the second one is somewhere there. Okay, you see here the two. Okay. Now, I think for the movies, unfortunately, this is the end. We need to start working. So let's stop here for the movies. We have done simulations that make that. It doesn't look like similar to the other one. So this is what our simulation does. The two sharks and we have been doing this through just basic population dynamics. You know, the fraction of people that live in and out is given by Kolmogorov forward equation in evolutionary games. Okay. Other applications are you can find in our website. I'm not supposed to talk about those things here, but we do have some applications in evacuation problems, routing, traffic video analytics, and so on and so forth. So let's get started. The first part of my lecture will be on differential games without Manifold. And then the second part will be with Manifold. Progressively, we'll add Poisson processes instead of Brownian motion. We'll replace and put some Poisson processes. We'll have common noise at some point, probably third lecture, and we'll have switching between different dynamics as well, all Markovian and external. Okay, so that will be the agenda. I would like to thank my co-authors, collaborators for this research, and also the US Air Force for their support on the Manifold games research. So the agenda for this lecture in particular is to define what a game is, what you already know, what is a Manifold type games, slightly different than Manifold games, and then the linear quadratic setup. So what is a game? We said that last week that a game is trying to analyze decision making and so on. So a game is given by a set of participants to the game. This is our what we call decision makers, players, agents, and so on, your favorite name. Then each of them has an action to choose. That action could be coupled with the action of the others. We haven't seen that part yet. It's called constraint games. If you go back to Arrow Debray in the 50s, the choice of an agent is coupled with the choice of the others. Then each of them receive a certain payoff function. The payoff, well, here is the loss function, is given by the choice, determined by the choice of all the agents. So U is action here. U is the choice variable. Okay, it's not the value function here. It's a choice variable. Okay, and then each agent is trying to minimize this loss function, given the choice of the other agent. So I'm changing only the component I here. That's what is called unilateral deviation. So if you change two components at the same time, it's bilateral, three components and so on, that's more involved. It's called strong equilibrium in that case. This is the weak formulation of it, the Nash equilibrium. Okay? So it goes back to Cournot. We usually, in France, we call it Cournot-Nash equilibrium because it was done by Cournot in the 19th century. So so Nash equilibrium for this audience, but once I'm out, I say Cournot equilibrium. Okay, so for differential game, you'll see that we might need to call Ross equilibrium because we have seen that he has done that as well. Okay, now in the previous model, you had a state dependence, means that your payoff function now depends on the state. It could be a common state. It could be individual states, all the states together. So this could be a vector of all the states of all the agents, if you prefer that. Okay? So the payoff function will depend on the state and the choice variable. And then you need to explain how the state changes. The next state depends on the previous state. You could include all the past states if you prefer that, and all the past choices. But the simplest version is the Markov structure. So you just go to the next state depending on where you are and what you are doing, what everyone is doing. The payoff does the same structure, and this was introduced by Shapley in '53. It's called stochastic games. Okay? You have a Markov structure here. The loss function was time dependent with some discount factor in his paper, and he was interested in the long-term discounted payoff. Two-player zero-sum games, and he has shown that there is a value, means the max-min is min-max, and so on. Now, what is Manifold type game is you take the previous model and you add some dependence in the distribution of the state on it, or distribution of actions, because a game is always given by the action of all the players, so that's, you could include also the distribution of actions. But the distribution of state will be the key thing because the action will be taken as a function of state and distribution, right? So the transition probability will also might depend on that distribution as well. Okay? Do you see any difference between Manifold games? So in Manifold games, we are going to freeze this because it's coming from infinite number of decision makers. In meaningful type games, you cannot freeze that. Why? Because this could be just your own state. I want to reduce the variance of my loss of my state, for example. It's my own state, so I'm influencing that state. So I cannot freeze that in meaningful type games. That makes the difference. Okay? And other thing, we can have meaningful type game with 2 players, 3 players, 4 players. It doesn't need to be infinite. Is it clear for everyone what's the difference between the two? Okay, so this is what we call Markin-Vlasov dynamics. If you freeze, it's not Markin-Vlasov dynamics. It's something else. Given a measure-dependent dynamics, given a measure, I solve this thing. Okay? So we'll consider a certain number of agents. This is the set of agents, 1, 2, 3. Well, to be honest, we'll have 4, 5. We don't go to larger than 5. The drift, diffusion, and regime switching will be considered later on. The loss function will be relatively general, but quadratic, at most quadratic. Let me briefly comment on information structure. You already had a comment by Tamer Bashar on that. So this one, so we discussed about open loop strategy, state feedback strategy. Now I'm going to, in the feedback, I will include a distribution on it. But I'm going to consider linear quadratic, so I don't need the entire distribution for this. So I will consider just the conditional mean of something. Okay? So that will be the state feedback, state and meaningful feedback. And closed loop strategy is the one that track the entire path. And the last one is extremely popular in differential games. If you look at differential games, we have something called randomized strategies, or random strategy if you prefer, with non-anticipative because we don't want to include the feature because we don't know it, with some small delays. So the last one will not be really considered except for existence, which we don't need because we are going to compute explicitly. So remember, open loop solutions and feedback solutions might be completely different in the context of games. Even in the context of control, they are different, but in the context of games especially, they will be completely different. And we will show an example with linear quadratic framework. So do you want me to go again in the strategies? Based on what you have seen, this is just a review of the things that we have seen last week. So maybe we could jump on it. One reference, the work by Robert Aumann on mixed strategies does this, what we are calling relaxed control last week. Well, that's in this paper. We call it randomized mixed strategies, behavioral mixed strategies. Okay? Now, Nash equilibrium is the same setup as before. From static to dynamic, there is no change in the definition of Nash. You just have to choose your information structure. That's the important thing. I will add one more thing, Bayesian Nash equilibrium, because we'll need it later on. So the Bayes equilibrium is this. You have the same model with types. Each player has its own type. You know your type, but you don't know the type of the other agents. Nobody will tell you his type. So you will have a belief or something on the type of other agents, and you are going to condition. So since your type is known, type of I is Zi, that is known, you condition on the entire distribution, the size will be given. You do that conditional probability and take the expectation with respect to that. And then take the expectation with respect to all random variables that are in and minimize that. That's Bayes Nash equilibrium. We'll see in an example, especially in the Kurno game, where the companies have their production cost imagine two interacting firms. They will not tell you their production costs because they are hiring people from cheap places and so on. They will not tell you their cost, right? So that will be their type, and you have to condition, and they put a belief on the type of other agents. That's the only concept that is new for you, for some of you. Okay, let's move on. The goal of the four lectures is to solve this basic problem. S is the state. The state solve this linear stochastic differential equation. Are you impressed? Okay. So you have a function of, this is B naught is a function of time, and switching, which regime you are. We consider a finite number of regimes, okay? So this is a function of time and the switching. B1 same, B1 bar same. S is the state, S bar is the conditional state, is the average if you prefer. I don't want to say it's stochastic right now. It's just the average, okay? S bar is the average of this state. You have the control input of all the agents. We don't have infinitely many. We have only n. Okay? If you change your own control here, it's going to affect the state. Therefore, it's going to affect the mean here. Okay? You do the same thing for the diffusion coefficients, and same thing for the jump coefficient. This is a compensated jump process. So we start from a random Poisson measure, and we remove the center part to make it compensated. And the initial state is independent with the Brownian motion and the jump. Okay? So that's your state dynamics. And you want to minimize this object. So it's a weighted sum of the variance of the state. That's important. Variance. The average is here somehow. So it includes mean variance problems, which are extremely popular for portfolio minimization. And it has also the square of the expected value. You do the same thing for the running cost, which include now covariance terms. Not just the variance, but also the covariance between the states and the control. Okay? So this is our goal. We want to solve explicitly this problem. Important, 0 PD till the end of my lectures. 0 SMP, stochastic maximum principle. Those are the two constraints, no PDEs, no maximum principle. All right, just solve it by hand, okay? So that next time you will be able to find solutions differently and compare with, for example, for checking your PDs. That's the idea. So remember now, B, the coefficients are linear. Big B denotes the Brownian motion. N is for jump. N tint is for the compensated jump. S tint is for switching. S is for the state. And this system is what we call conditional Markin-Vlasov because of the conditioning. But without that, it's the Markin-Vlasov system. It's different than the one where we go and freeze the measure. These dynamical systems driven by fixed measure. It has a name in the literature. Right? Those are two different things. Liouville systems. Any questions so far? Okay. So if we are all at the same page, we can move on the introduction, basic introduction to differential games. I forgot to mention, we will do the discrete time version of it as well, because some of you are maybe discretizing all the schemes, and you might end up to this case if you discretize with some step size. Okay? But in the discrete case, discrete time case, the process I'm going to consider is much more general. I don't need to be Brownian. I don't need any stochastic calculus for it. So this could be any process with second moment to be finite, because I'm minimizing this. So that's second moment to be finite, right? And we will be able to solve this. Well, if it's independent, you could quickly solve it. If it's correlated with S, means this process to be correlated with S, it's more involved, but you could still solve it if second moment is fine. Okay? So that's the difference. In the discrete time, you could solve for more general processes than just restricting to Brownian motions or Poisson. Okay, so continuous time and then discrete time. No PDEs, no Bellman equation, no Lagrange multipliers. How are you going to solve stochastic games that way? These are some of the techniques that we found in the literature. So of course, you found this. Dynamic programming is there. If it's Markovian, but if it's not, you could enlarge it and you could find a space for which it is Markovian. You could always do that. Maximum principle. So these two will not be allowed. Okay? This is just as we have been doing for polynomial expansion or Fourier series. The equivalent of this for random processes, at least for Brownian driven things, is called Wiener-Chaos expansion. And you enter that, you get deterministic equations, and you want to solve that. So that will not be allowed here either. We are going to employ this one, the last one, direct method. I added this because that's not science, but but since everyone is talking about it, I put it there. Okay. Okay. So we have done a survey, and I will tell you the results of the survey. This is not science either. Asking grad students what type of problem they use to solve optimal control or game or things like that. So the big percentage of them is saying that I do approximations. I don't care on PDEs. I don't care on Quadratic maximum principle. I just do approximations. The big part of them. That's not good sign for us. But if with the direct method, we will change that curve. So some of them are doing PDEs, some of them stochastic PDEs, even maximum principle or stochastic maximum principle. And there are, of course, other people who are, I don't know, they do deep learning with something else. I don't want to go there now. But this survey is interesting because if somehow I can give you a framework where you could test those things using direct method and then bring back and compare with numerical schemes that you are doing, then all this thing will change and you'll see the big proportion will be connected to those two. So that's the goal. It's more educational framework than something else. So remember, no PDEs, no SMPs. So how are you going to solve the problem with direct method? We start with the expression that is there. First, Manifold free. So the agenda will be with Manifold free first, and then we go to the Manifold type games, and later on we'll have some introduction to competitive games. These are competition and cooperation together, because we are tired of the non-cooperation at some point. We will bring competition and cooperation together. Cooperative competition or competitive cooperation at some point, lecture 3 or 4. And the last one is to discuss things that we could do if it's not quadratic. I promise it will be always quadratic, but yeah, okay. So the recitation will be on the paper I've just shown you in the beginning. So I will review basic linear quadratic games. And lecture 2 will be on Manifold type version of it, recitation with the Manifold type. And the third lecture will be on competition, Nash bargaining, which is different than Nash equilibrium, and other cooperative concepts, psychological behavior, empathy problems, and so on. And the last one will be discrete time and beyond linear quadratic. So are you ready? Okay, so first lecture. I will start with the no diffusion case, deterministic. And then I will add some Brownian motion on it. So these two will be with one agent, one player game or optimal control if you prefer. And then I will include more than one agent. Deterministic again and then stochastic. Okay? These are basic, so we will just use integration formula, basic fundamental and theorem for calculus to find the solution. So the loss function for one agent, so consider one agent is not zero here. It has this cost functional. And the state is subject to, so the derivative, time derivative of the states is this U naught. U naught is the action, the control action. There is no constraint on the domain, so agent can choose any number. You are free. Okay? And you want to solve this problem. You want to minimize the cost function subject to this. No Bellman, no Pontryagin. So what do you do? Okay, it's similar to what Diogo was explaining. So look at the dimension of this. If this is linear in S, then this will be quadratic. This will be quadratic, so they are all quadratic. So I can take answer that is quadratic, run it, and identify my coefficients. So this is our answer. The guess, this is our guess. I mean, it has that shape. So you write that this alpha times S squared is equal to that function at the initial time plus the integral from 0 to t of the derivative of it. So alpha dot S squared plus the derivative of S here. So 2 times alpha. The derivative of S is given here. Right? U naught is the derivative of S. Okay, then you make the difference between our cost functional and our candidate. The candidate is at 0. You need to come backward, right? So the difference between the two cost function, you write, you replace the expression above here, and then you can write it as the terminal, the difference between the terminal coefficients. Here is a quadratic term. We have done a square completion of it. And here we have some other coefficient S squared. So that's the difference between the two expressions. Now we are going to minimize L naught, this function. Okay, so it means minimize the last part because this is just a number. Where is U? U naught is only appearing here. You want to minimize this quadratic thing. Well, set it equal to 0. You do that, and you get optimal control here. The value function, so set this one to 0 and the last term here to 0. So your value function is this one. It's just that. If you understand this, all the rest is replicating this again and again and again. So there is nothing mysterious. This is very basic for you guys here. So the optimal cost, as I said, is given by the expression at time naught. The optimal control is here. And remember the discussion on if it is plus or minus, you get finite time blow up. Okay, you could see it here. Alpha of t is this. If q is negative, if q naught is negative, then this term is less than t. You get a blow up before 0. I mean, you start at time capital T. Before arriving to 0, there is a blow up here. If this term is negative here, right? But if this term is positive, then there is no blow up. Well, the blow up is supposed to happen after time t, but you are not going there, right? So remember, we will have a lot of Riccati equations. They might have finite time blow up if we don't care on the coefficients. Okay? So this is our state dynamics. Alpha of t is here. You plug here 0, and then you get the value function that is here. Okay? First, explicit expression for our value without dynamic programming. So this is what we call direct method. Okay? It's just doing a verification method for. We used to do, in the verification method, we used to do the same thing. But here it's just taking that part and remove all the rest, the technicalities. Now, one comment, if the control action is constrained, I mean, constrained means limited for us, okay? Instead of the entire domain, be careful. If this domain is not convex, you might go into big issues of non-existence of pure strategies. It's something that is very well known. So we have already seen last week on this example. So example, so you want to minimize this quadratic state. Oh, okay, that one. And there is no pure strategy that is optimal, but there is a randomized strategy that's optimal. The randomized version is this, where you have to choose two numbers that sums to 1, so it means one number. And this is now your new state dynamics, and you minimize this. Well, if you start at 0, then you could choose those numbers to be 0 all the time, and s equal to 0 minimizes here. If you are a fan of literature, go back and look at it here. Relaxed control is there. For the colonel blotto games. That game means you have two opponent. So it's a game is army, okay? If you send if the number of soldiers you send to a specific place is more than your opponent, then you win that gun, and so on. Okay? And there is no pure equilibrium there, and he introduced a relaxed control there to find the equilibrium. I stop here for this comment. Now, let's move to the stochastic case. So I take the previous example, but now I add a diffusion coefficient here, sigma. This is the Brown motion. And I modify a bit the cost. Now it's expected value. I could consider a risk-sensitive version of it. For this problem, we'll be able to solve as well. But let's start with the risk-neutral case. So expected value of the loss function, because now S is stochastic. So we want to solve this problem. Again, same technique as before, but now a bit of Ito calculus. I couldn't avoid it at some point. You will have this extra term, sigma square, so divided by 2, second derivative. So that will end up to alpha, right? The 2 coming from the second derivative and the 2 of the sigma square, and then you get this term here. And this is the derivative of, so these 2 terms are added to in the Ito's formula. And the other is the same thing, except that you'll have this thing remaining and this extra thing. Okay? The optimal control, is the same as before. The optimal cost has changed because I have this extra term. This is gone because this is martingale stuff. So this is gone. So the optimal cost is the initial year term there and the last thing, yes, integral of sigma square, if sigma depends on time, which I didn't specify, but it doesn't matter. Okay? So you could extend from the deterministic to the stochastic, the same technique. Any question on this? Okay, so let me write it here. Yeah, so f of t is equal to f of 0 plus integral 0 to t f prime, whatever. This is what we are doing. F of t equal to f of 0 integral of the derivative without the, just that. Yeah, but I don't have co-states and all these things. It's a verification, I told you. So just plug your answer and apply Ito's calculus, and you get the results. You don't need to go into co-states and all these systems. Right? Okay. We are going to generalize this when the diffusion coefficient is state dependent, control dependent, and so on. So the optimal control, the optimal value, as I said, is the previous one plus this term, if you have sigma on it. That is a small change. If sigma is 0, you are back to the previous problem. The optimal control is in state feedback form, means you need the state at time t to get it. Alpha is offline, it's solved offline. You don't need anything to run this alpha. And we have solved this alpha explicitly, by the way. So the state is now stochastic with this extra term here because of the Brownian here. Okay? So explicit. References for this. So last week we had the chance to have Professor Duncan, who is one of the first person to work on direct methods, linear quadratic with general noise processors. I added some of his references there. And he has done also the resensitive versions of this in a couple of papers. Okay, so these are mean-field free, and we are going to extend them to the mean-field dependent case, mean-field type game case. Okay? If it's not quadratic, he was still able to do actually a lot of cases that are not quadratic, as Diogo mentioned this morning, the logarithm case. He has done also for on the torus, he was able to find with sine functions, and so different extensions, and the fractional Brownian motion case as well. Okay, so now I will give you an example of linear quadratic, because I feel like people say this is simple. Let's see the simple example here. 2 stages. So there will be a game with 2 players, and it will be played over 2 stages. Stage 1. A random process, his realization is observed by player 1. Okay, y is observation. So x is the realizing, y equal to x naught means you observe the state and you decide u naught. That's at first stage. After deciding, you get this cost to pay. Okay, a number here, non-zero, positive number, u naught square, quadratic, right? At stage 1, the state is given by this formula here. You observe y, but y is a noisy version of it. Okay? Noisy version of x. So you don't see x, you will see only y, the output of y. You decide u1, and there is no cost to pay. You don't observe anything or no thing to pay. Now, after your decision, new output, but you don't see anything because the game is over, but there will be a terminal cost on it. The cost, the total cost, is the sum of all the costs here. You want to minimize that cost. It's random. These terms are random, x naught and w1. That's why we want to consider expected value of it. You want to solve this problem. You are allowed to choose control actions that are dependent on what you know. And what you know is the observation. Okay? u naught of y naught, u1 of y1. Choose those functions such that the total cost here is minimized. So this was introduced by Wiesenhausen in the 68. And it's linear quadratic, right? Because this here, the sum here is everything is quadratic. These things here are linear. Look at it on the internet. You'll realize this is an open problem. It's linear quadratic. It's an open problem. What's the difference between what you do? Partial observation is key. So the information structures will enter into it, and it becomes nonlinear, actually. He was able to show in that paper that there, for some distributions of x naught, there is no linear policy that is optimal. So the problem is linear quadratic, but the solution structure is not linear. And extensions by Tamer Bashar here. When is it linear and when is not? When is linear policy optimal or not, and so on. That's why they introduced the quantized strategy that we were discussing last week. Okay, so linear quadratic setup with partial observation where the optimal control is an open problem still today. So not everything is solved in the linear quadratic. This is what I want to mention. So we could extend the framework to, let me, one sec. The same technique you could extend to arbitrary number of players. So first deterministic case, but now I add n agents. This will be useful in the recitation because we'll consider that framework. The cost function is similar as before. Now there is index I, means for each agent we might have different coefficients. The initial state is given. And you want to solve the best response problem. You want to, each agent is minimizing its own cost, subject to that common state. This is a common state for all the agents. Same technique, no change. Run that, you get the optimal control in this form. You get the optimal cost in this form. The optimal control is linear state feedback. Now there is a change. Because you have multiple agents, you get this term here. You get the alpha of the other agents involved in your alpha. The interaction comes here. If it's optimal control, means one agent, you don't have this because there is no other agent. Right? Now, if you solve with von Driehagen maximum principle, because you are fan of that, you will not get this term. You'll get another equation here without the 2 in particular. It's suboptimal if you work with open loop. You don't see it in the optimal control because you get the same control law, you get the same value, so you are happy. But just for this 2-player, you look at open loop and state feedback, you get different solutions. You could compare the costs if you prefer. So you can find some of this, this is one dimension, S is one dimension. You could generalize to the matrix case, S to be a vector and so on in the book by Tamer Bashar in the 82. There is a second edition in 99 of this. Okay? You can extend to the stochastic version of it by adding your diffusion coefficients, and now we'll add a Poisson processor. And the cost function, because of the Poisson, is slightly modified, but there is no big change. The optimal control stays as before because these are state independent. So later on, we'll include here the state, the control actions, expected value of state, expected value of control actions. Then this is not valid anymore. You get different things. Okay? One more comment, semi-explicit, because I still need to solve this. It's an ODE. Right now it's simple, but it gets more and more involved because of the dependence of the other coefficients. The existence of positive solution to this require conditions on those things. Q to be positive. Okay, that's reasonable, because if you are negative, you can make this one minus infinity. Qi to be positive. You need the term here to be positive, so Ri to be positive. Well, that's a reasonable thing. Again, because if it's negative, you can make it minus infinity. Okay? So for matrix versions, it needs positivity, non-negativity of those matrices and of non-symmetric Riccati equations. To derive this explicit, go back and use Ito's formula. So your favorite question is now here. You apply Ito's formula, this formula, with your answer, and you get the coefficients. There is no other thing. There is no, except a square completion at some step. Okay. For the Ito's formula, I prefer to give you references only because it makes my life easier. I don't go into the martingale and show that, okay, there is no jump there and here. No, I give you the formula and I apply it. Any question, comments? We are not too fast, we are not too slow. So one last comment and then I will conclude. So the method, the direct method works as follows. We start with the guess functional, I said. Then the previous formula is used. Square completion, because I am minimizing. And then process identification. It's a verification technique, so there is no other optimality thing to check because I'm minimizing a quadratic thing. I set them to 0, and that's it. So we try to teach this to undergrad students, differential equations, without dynamic programming, without Bellman, and claim that it's simple. I don't know if it is that simple, but so far, if they know the fundamental formula for calculus, and in the stochastic case, the Ito's is admitted, then they could really solve this thing without involving into PDEs or maximum principle. Okay? Simple. At least they start understanding the framework. That's good news. And they get semi-explicit solutions with the solver for the ODEs. But it's at most quadratic thing there as well. Recitation will be on the model by Rosen.